Speed comparison with Project Euler, C versus Python versus Erlang versus Haskell. I have taken problem number 12 from Project Euler as a programming exercise and to compare my, surely not optimal, implementations in C, Python, Erlang and Haskell. In order to get some higher execution times, I search for the first triangle number with more than 1,000 divisors instead of 500 as stated in the original problem. The result is the following. C. Python. Python with PyP. Erlang. Haskell. Summary. C. 100%, Python, 692%, 118% with PyP, Erlang, 436%, 135% thanks to Richard C. Haskell, 1421%. I suppose that C has a big advantage as it uses long for the calculations and not arbitrary length integers as the other three. Also it doesn't need to load a runtime first, do the others? Question 1. Do Erlang, Python and Haskell lose speed due to using arbitrary length integers or don't they as long as the values are less than maxent? Question 2. Why is Haskell so slow? Is there a compiler flag that turns off the brakes or is it my implementation? The latter is quite probable as Haskell is a book with 7 seals to me. Question 3. Can you offer me some hints how to optimize these implementations without changing the way I determine the factors? Optimization in any way, nicer, faster, more native to the language. Edit. Question 4. Do my functional implementations permit last call optimization, aka tail recursion elimination, and hence avoid adding unnecessary frames onto the call stack? I really try to implement the same algorithm as similar as possible in the 4 languages, although I have to admit that my Haskell and Erlang knowledge is very limited. Source codes used.
Using GHC 7.0.3, GCC 4.4.6, Linux 2.6.29 on an x86_64 Core 2 Duo, 2.5 GHz machine, Compiling using GHC02 FLLVM force recomp for Haskell and GCC03 LM for C. Your C routine runs in 8.4 seconds, faster than your run probably because of O3. The Haskell solution runs in 36 seconds. Due to the O2 flag, your factor count code isn't explicitly typed and defaulting to integer. Thanks to Daniel for correcting my misdiagnosis here. Giving an explicit type signature, which is standard practice anyway, using it in the time changes to 11.1 seconds. In factor count you have needlessly called from integral. A fix results in no change though. The compiler is smart. Lucky for you, you used mod where RAM is faster and sufficient. This changes the time to 8.5 seconds. Factor count is constantly applying 2 extra arguments that never change. Number, sqrt. A worker/wrapper transformation gives us That's right, 7.95 seconds. Consistently half a second faster than the C solution. Without the FLLVM flag I'm still getting 8.182 seconds, so the NCG backend is doing well in this case too. Conclusion, Haskell is awesome. Resulting code. Edit. So now that we've explored that, let's address the questions. Question 1. Do Erlang, Python and Haskell lose speed due to using arbitrary length integers, or don't they as long as the values are less than maxint? In Haskell, using integer is slower than int, but how much slower depends on the computations performed. Luckily, for 64-bit machines, int is sufficient. For portability's sake you should probably rewrite my code to use int64 or word64. C isn't the only language with a long. Question 2. Why is Haskell so slow? Is there a compiler flag that turns off the brakes, or is it my implementation? The latter is quite probable, as Haskell is a book with 7 seals to me. Question 3. Can you offer me some hints how to optimize these implementations without changing the way I determine the factors? Optimization in any way, nicer, faster, more native to the language. That was what I answered above. The answer was 0. Use optimization via O2. 1. Use fast, notably, unbox able, types when possible. 2. Rem not mod, a frequently forgotten optimization. And 3. Worker/wrapper transformation, perhaps the most common optimization. Question 4. Do my functional implementations permit WCO and hence avoid adding unnecessary frames onto the call stack? Yes, that wasn't the issue. Good work and glad you considered this.
There are some problems with the Erlang implementation. As baseline for the following, my measured execution time for your unmodified Erlang program was 47.6 seconds, compared to 12.7 seconds for the C code. The first thing you should do if you want to run computationally intensive Erlang code is to use native code. Compiling with Erlang plus native Euler 12 got the time down to 41.3 seconds. This is however a much lower speedup, just 15%, than expected from native compilation on this kind of code, and the problem is your use of compile export_all. This is useful for experimentation, but the fact that all functions are potentially reachable from the outside causes the native compiler to be very conservative. The normal beam emulator is not that much affected. Replacing this declaration with export solve/0 gives a much better speedup, 31.5 seconds, almost 35% from the baseline. But the code itself has a problem. For each iteration in the factor count loop, you perform this test. The C code doesn't do this. In general, it can be tricky to make a fair comparison between different implementations of the same code, and in particular if the algorithm is numerical, because you need to be sure that they are actually doing the same thing. A slight rounding error in one implementation due to some typecast somewhere may cause it to do many more iterations than the other, even though both eventually reach the same result. To eliminate this possible error source, and get rid of the extra test in each iteration, I rewrote the factor count function as follows, closely modeled on the C code. This rewrite, no export underscore all, and native compilation, gave me the following run time. Which is not too bad compared to the C code. Considering that Erlang is not at all geared towards writing numerical code, being only 50% slower than C on a program like this is pretty good. Finally, regarding your questions. Question 1, do Erlang, Python and Haskell lose speed due to using arbitrary length integers, or don't they as long as the values are less than maxent? Yes, somewhat. In Erlang, there is no way of saying use 32/64 of a bit arithmetic with wraparound, so unless the compiler can prove some bounds on your integers, and it usually can't, it must check all computations to see if they can fit in a single tagged word or if it has to turn them into heap-allocated bignums. Even if no bignums are ever used in practice at runtime, these checks will have to be performed. On the other hand, that means you know that the algorithm will never fail because of an unexpected integer wraparound if you suddenly give it larger inputs than before. Question 4. Do my functional implementations permit LCO and hence avoid adding unnecessary frames onto the call stack? Yes, your Erlang code is correct with respect to last call optimization.
In regards to Python optimization, in addition to using PyPy, for pretty impressive speedups with zero change to your code, you could use PyPy's translation toolchain to compile a Python-compliant version, or Cython to build an extension module, both of which are faster than the C version in my testing, with the Cython module nearly twice as fast. For reference, I include C and PyPy benchmark results as well. C. Compiled with GCC 03LM. PyPy 1.5. Python, using latest PyPy revision, C2F583445E. Cython 0.15. The Python version has a couple of key changes. To translate into a standalone program, you need to define your target, which in this case is the main function. It's expected to accept sys.argv as its only argument, and is required to return an int. You can translate it by using translate.py, %translate.py Euler 12 or python.py, which translates to C and compiles it for you. The Cython version was rewritten as an extension module _Euler 12.pix, which I import and call from a normal Python file. The _Euler 12.pix is essentially the same as your version, with some additional static type declarations. The setup.py has the normal boilerplate to build the extension, using Python setup.py build _ext in place. I honestly have very little experience with either Python or Cython, and was pleasantly surprised at the results. If you are using Python, writing your CPU-intensive bits of code in a Cython extension module seems like a really easy way to optimize your program.
Question 3. Can you offer me some hints how to optimize these implementations without changing the way I determine the factors? Optimization in any way, nicer, faster, more native to the language. The C implementation is suboptimal, as hinted at by Thomas M. Dubuisson. The version uses 64-bit integers, i.e. long data type. I'll investigate the assembly listing later, but with an educated guess, there are some memory accesses going on in the compiled code, which make using 64-bit integers significantly slower. It's that or generated code, be it the fact that you can fit less 64-bit ints in a register or round a double to a 64-bit integer is slower. Here is the modified code. Simply replace long with int and I explicitly inlined factor count, although I do not think that this is necessary with GCC 03. Running plus timing it gives. For reference, the Haskell implementation by Thomas in the earlier answer gives. Conclusion, taking nothing away from GHC, it's a great compiler, but GCC normally generates faster code.
If you want to see more, please consider subscribing.